Hi, I'm Will Soloway, and I'll be talking about the current and future status of gaseous hydrogen storage. With the use of fossil fuels and non-renewables becoming increasingly unpopular sources of energy, the transition towards an alternative fuel is becoming more prominent. Hydrogen presents an alternative solution to the problem, having an energy content of 120 megajoules per kilogram, which is far greater than that of other fuels such as methane, gasoline, or diesel. Current methods of hydrogen containment are in the forms of high-pressure storage tanks, which come in the form of 4 different tank types, often stored between 350 and 700 bar. Each tank type varies on its material and application, with Type 1 being a seamless metallic container, Type 2 being a seamless or welded hoop wrap container, and Types 3 and 4 being polymer-lined containers with a matrix overwrap, often made of carbon fiber. Tank construction is based mainly around conformability considerations, which are split into the following: filament winding, macro-lattice vessels, and replicant conformable vessels. Therefore, the aims and objectives of this paper is to carry out a critical review into the codes and standards, health and safety, conditions, and costs associated with high-pressure storage. These aims will be met using a material simulation selection using EduPack, as well as an analysis into the current research with tank liner materials using the methylated reaction of the monomer spirobicidane to produce 3 derivatives, PIM1, MEPIM65, and MEPIM150. The results are split into 2 sections, that being the material simulation and the polymeric derivative assessment. The results of the simulation gave 4 materials that satisfied the characteristic criteria, those being cast iron, high, medium, and low carbon steel. The results of the PIM study revealed that the MEPIM 150, which is the methylated PIM produced at 150 degrees, gave the highest microporosity and therefore the best hydrogen absorbance. To conclude, the results of the simulation showed a limited number of materials available for the tank construction, with the characteristics of Young's modulus, Poisson ratio, and maximum and minimum service temperature being tested on EduPack. The results of the PIM study showed that hydrogen uptake rose with an increase in pressure, with the methylated PIM polymer produced at 150 degrees being the most absorbent. The molecular conformability of the vessels is still an area that needs to be addressed, particularly with non-spherical or non-cylindrical vessels. Also, more research into efficient lining materials is required for higher storage capacities.